Okay, hi, this is lesson 7.1, exponential functions. On exponential functions, you need to be familiar with the form of it, which is this right here, where the initial value is the a, the number that's in the front. The b, the one that has the exponent, is either a growth or decay factor depending on its value. And x is an exponent. So you need to be familiar with the form of it and what values represent what to answer all of the questions that you're going to have on this. The next two pieces here, this is what the graph looks like for the exponential growth. This is what the graph looks like down here for the exponential decay. It looks like for the exponential growth it grows without bound on one side, and it does. But I want you to realize that it is actually growing away from the asymptote. Okay, so it can be flipped around the other direction and still be a growth, even if it's flipped. The graph of the decay, it decays toward the asymptote. It's getting closer and closer to the asymptote. So notice how this one, yes, I know it goes down, but it's getting closer and closer to the asymptote. Here it's going away. So you just got to notice the difference, because that comes up in some of the other questions. Now on this page, they're wanting you to recognize or be able to identify if it is growth, decay, or neither. So when we're looking at these particular things, let's see, on these graphs, and of course it's wanting you to do it on your own, you just have to remember that if it's going away from the asymptote, then it's a growth, even if it's upside down, okay? And if it's getting closer then from the asymptote, then it's decay. So when I look at the pictures, this graph is getting closer and closer to the asymptote, so it's decay. This one, the asymptote is obviously right here, so this is also a decay on that one. This graph, even though it's going down, notice how it's getting further and further from the asymptote. The asymptote, horizontal asymptote, would be there. So this is actually a growth on this one. Okay, it looks backwards, but it's not. This one is growing up. It's going away from the asymptote. The asymptote is obviously right here, so that is also a growth. Now, this piece right here is a trick question. That is a neither. This is actually a logarithmic graph. You're going to learn more about that soon. As far as equations go, I want you to realize that this equation actually is a growth equation. At first, when you look at it, it seems like it would not be because of that fraction is less than 1. But because we had this negative exponent, if we rewrite this as y equal to 0.4, and we make this exponent be positive, remember we do the reciprocal, so this would be 10 over 7. So now that's greater than 1, so that is actually a growth equation. So don't let it trick you. Sometimes it will. All right, this next one right there, that is neither. Yes, that is neither growth or decay because it's not even exponential, because it's quadratic. That x is not an exponent. So the exponential ones, the x has to be an exponent. On this next one, this is a growth because that 2 is bigger than 1. This one has a 2, but notice it's got a negative exponent. So that actually is the same thing as saying negative and then 1/2 to the x power. So it's actually a fraction, so it's less than 1. So this is a decay. So they're just wanting you to be able to recognize it. It comes up in questions like on ACT and stuff like that. So if you can recognize it, that's great. Now as far as graphing, I don't think I have any graphing on the test. Actually, let me look right now while I got it out. No graphing on the test, yay. But I just kind of want you to know what it looks like and be familiar with it. They all have that same basic shape like what you saw on the other page. So if you were going to graph this, you could just simply make a chart, -2 to +2 like we usually do, and then plug those values in the equation. And if I clean it up, I get rid of that negative exponent right there. I'm doing the reciprocal, that 1/2, so it's 2 to the x power. So if you do that, you get 3/4 here. This is 3/2. This is 3. This is 6. This is 12. And you could just use your calculator if you need to, or we're just plugging it in. In class, we actually did it all the way. Okay, so -2 3/4, 1/2 at -1, 0 is 3, 1 is, oh wow, that's off my graph, huh? Okay, so it actually looks like this, okay, and it skyrockets that way. So there is an asymptote at x equals 0, always. Okay, so we know our domain, well, it's all real numbers. And we know the range, well, y has to be greater than 0. It can never be 0. It's greater than 0 because there's an asymptote at y equals 0. This is actually an example of a growth. But if you notice, they all have that same shape, whether they're going away from, it's moving away from the asymptote or it's moving closer, depending if it's growth or decay. Okay, so on this page is where it actually gets interesting because we're starting to use it. And most of these exponential functions is basically just using the formulas and things like that. So notice on the top we've got our compound interest formula, which is this one, okay? And they tell you what all these things mean. You basically should know this. You should memorize that, okay? And that's for, see, T is time, P is the principal, which is your initial investment. R is your annual interest rate. N is the number of times the interest is compounded per year. A is what you end up with after. If you have it continuously compounded, then instead of using N, you actually end up with using E because it merges to that, which eventually we'll look at that in a little bit more detail. But for now, that is it. You hear it called PERT sometimes, but that's not actually probably correct. So those two are used a lot, okay, in finance and in business. Now, this other part is growth and decay models. That's this one. This is like a generic one that you can use for a multitude of things, okay? So the compound interest and the compound interest ones are specific when they're dealing with money, okay, and interest rates and things like that. The good thing is on this, you do get to use a calculator to figure it out. You see the little calculator thing, so that's pretty cool. But and sometimes it's hard to figure out how to plug it in the calculator. So if you need help with that, you're going to have to see me in class, and I will certainly help you with that. So on example 4, you deposit $3,000 in an account that pays 3.28% annual interest. How much would you have if the interest was compounded daily for 5 years? And then again, continuously. So we're going to do it twice. We're going to do the first question. If we're compounding daily, so that means I got to use this one. Okay, so this would be A is equal to P. P is our amount we're investing. So we're investing $3,000. And let's see, then it's parentheses 1 plus R. R is our interest rate. Well, that's 3.28%. So you have to write it as 0.0328. Okay, you got to change it to a decimal. Divided by N. N is the number of compoundings paid per year. So how often? Well, it's daily. How many days are in a year? You're right, 365, okay? And then, and we have to the NT power. So that's to the 365 times, how many? 5 years. Okay, so T is 5. So you have to be real careful when you put this in your calculator. You either need to work this part out first and get a value, and then just type it all in one fell swoop, or depending on what calculator you use, as long as you put parentheses around the 365 times 5, you're okay. But I want you to actually do it on your calculator yourself. You should get the value, and you do have to, make this look like money, so you got to round it to the nearest penny, hundredths place. You should get this value. So just plug it in, make sure you get that. If you don't, ask me and I'll show you how to do that. Okay, so for the next part, continuously, If you're doing continuously, you have to use that formula, okay? That's the one with the E, because you don't know what n is. It's continuous. So, and I'm going to write it just over here on the side because I'm writing kind of big. So it's 3,000 for our P, e to the RT power. So the power is 0.0328 and then times 5. And I'm running out of room over here, times 5. Oh, goodness, let me put it in. So again, just be real careful how you put that in your calculator. Make sure you're actually using the proper one for the E right here. Okay, there is an E button. It's right at the LN. I think it's the same one with the LN. You have to hit like the second key or something to get there. So just make sure you're getting the right value here, and that should give us 353464. I suggest you plug that in your calculator to make sure you're getting it right so you know how to put it in. All right, number 5, the relative growth rate for bacteria from Sully's tongue is 80% per hour after eating a Turkish pizza. Gross. Sully swabs his mouth and starts a culture that 4 hours later shows approximately 50,000 bacteria. How many bacteria did Sully start the culture with? Okay, so notice this is not money. If this is not money, then that means we're using our generic one up here. So we have y equal to a parentheses 1 plus or minus r to the t power. Okay, so we're going to figure out what is what here. Okay, so y is what we're starting with. No, a is what we're starting with. That's the initial value. That's what we're looking for, right? Because it says how many bacteria did Sully start with. So a is what we're looking for. Y is what you ended up with. So 50,000. Oh, Wally, that's a big number. 50,000 is equal to A times 1. Ooh, is it plus or minus? Let's see. Well, is the bacteria getting more or getting less? You're right, it's getting more because it's a growth, so that's a plus. R is our interest rate, or I'm not interest rate. That would be the other. R is our rate of change. Let's see. 80% per hour, so 0.08. I guess it is kind of a percent. And T time 4 hours. All right, so now I just got to solve for A. So I'm going to do that over here. So 50,000 equal to A times 1.8 to the fourth power. So if I divide by 1.8 to the fourth power on both sides, I get A is about 4,763 bacteria. And notice it's less than what we started with, but it should be because that's the beginning. That's where it all started. Okay, so now on the next part. This is actually where you're solving equations with exponents, but these are the easier ones. I mean, dare I say easier. You need to be able to remember your exponent rules and what we've had before, okay, and what you've done before. So, oh, wow, let's see if I can make this larger. Okay, so for instance, see if you can write this in the same base. Well, same thing with the 9. Write these as the same base as the 3. If I can get it the same base, then I can clean it up. So I know this would be 3 to the x squared over 3 to the third equal 3 squared, well, and an x right there. Okay, so notice I wrote them all to have the same base. If you write the same base, you don't have to use the log properties to get there, which we don't know yet. Okay, so at this point, I can clean this up some more and get it to be just 1, 3 on the left-hand side. Because remember, this is where you subtract your exponents. So we have 3 to the x squared minus 3 equal 3 to the 2x. Now, when you have the same base like that, you can use your 1-to-1 property. So this means we have x squared minus 3 equal to 2x. And because it's quadratic, I can just put it all on the same side, equal to 0, and solve. Let's see, that factors to x minus 3, x plus 1. So I'm going to get 2 answers, x equal to 3 or x equal to negative 1. Sweet. Okay, so let's look at number 7. On this one, 64, 64, and 4. Well, I know 64 is 4 to the third power. So I'm going to write this as 4 to the third power. This one would be 1 over 4 to the third power. And that's, of course, 4 squared. So we have 4 to the negative 9w. Remember, that's where you multiply it. Times 4 to the negative 3 power. Now I can add those exponents, but I can't actually add them because they're not like terms. But I can make it have one, the same base on both sides. So now that I have the same base on both sides, use my one-to-one property. Negative 9w minus 3 is equal to 2. So negative 9w would be equal to 5. So w is a negative 5/9. That's a weird answer, but that is it. All right, so let's look at the next one, number 8. Now it says you try, so if you want to pause the video and try it yourself, you certainly can. I see we have 16 and we have 4, and 4 squared is 16. So this actually would be 4 squared to the 2r plus 3 power times, I'm going to go ahead and just write it as 4 to the negative 2 to the 2r power, 4 to the r power. So this will be 4 to the 4r plus 6 times 4 to the negative 4r. So if I add those exponents, oh wow, that gives me 4 to the 6 equal 4 to the r. So r has to be 6. That wasn't so bad. All right, very good. Okay, so the rest of these are homework problems for you to do on your own. I found that people did pretty good on these on the first part, so I'm not going to put that on the video, but I'm going to explain number 7 and number 8, and then go on from there if you need those, and I will post these answers also so you'll have it to check. Okay, so on number 7, so let's just look at that one. Number 7, the website bankrate.com publishes a weekly list of the top saving deposit yields. In the category for a 3-year certificates of deposit, the following were listed. Which bank should you choose for a $5,000 investment? Decide by completing the table. Okay, so here they're compounded. This one says quarterly, daily, monthly, and then continuously. And they all have different interest rates. So you want the one that's you're going to make the most money, right? That's the whole point. So these 3, you need to use the formula A equal to P times 1 plus R over N to the NT power, because that's the one that you're going to put the number of compoundings per year. Okay, so if quarterly, well, there's 4 quarters in a year, so that you would put in 4 for N on that one. Daily, you would have to put in 365 because there's 365 days in a year. Monthly, yeah, you're right, you would put in 12 because there's 12 months in a year. Now this next one here, continuously, you would have to use the PERT formula, P-E to the RT power, because there's no number really for continuous. So that's where it merges on using E, which is an irrational number. It's about 2.71, whatever. But anyway, so you got to use the other formula for it. Your initial investment on all of these is going to be P. Okay, so all of these, this is your P value. And your interest rate, you're just going to remember to change it to a decimal. So in other words, you're moving the decimal 2 places like that, okay, when you're plugging it in. And T is your time. Let's see, what is the time? Time is 3 years. It tells us right here. So you're going to put a 3 for T in all of them. So what I want you to do is use your calculator, plug it in. This is the values I got, and you can just look and see, did you get the same thing? And if not, let me know, and we'll figure out who's wrong, whether it's me, whether it's you. Is it just how we're putting it in the calculator? Because, different calculators, you put it in differently. So just check with me and see if you don't get those values. Okay, so now number 8, find each missing value in the table. So on this part, what you're needing to do is understand what the equation actually is. Remember our equation for the general form was y equal to, let me see. Let me pull it up right quick, make sure I'm writing down the same thing. A parentheses 1 plus or minus r to the t power, okay? So if you remember, if you look back at your notes at what we had on this, y is what you ended up with, a is what you started with, it's growth or decay, that's denoted by what's in the parentheses there, and the x is basically your t, okay, at the time at the end. So your initial value is always going to be, the initial value is always going to be what's right there, okay, what they start with. So on all of these, our initial value is this piece. So that's what you put in all of these places, okay? So that means when you get to this, that's what you're putting in that same location, okay? Notice y is in the same place, the equals are in the same place. Now looking at the other part, how do you know if it's growth or decay? Well, this part depends on what's inside of here. So if you have a number that's greater than 1, it's a growth. If it's between 0 and 1, it's decay. So notice that if I say 1 minus 0.25, that actually gives me 0.75, right? That's 3/4. That's less than 1. That's why this is a decay. So what does that mean exactly? Well, notice that when we're setting this down, it ends up being 1 minus r of 25%, so it's a loss of 25%. So that's where that's coming in, okay? It's a loss because it's a minus of 25%. Now, not all of them are separated like that. So, for instance, in this next one, where you have 1.25, that is obviously, if we rewrote it, 1 plus 0.25. So it's a gain of 25%. You can tell because it had to be added because it's bigger than 1. If it's bigger than 1 in that parentheses, it's obviously a growth. So as you keep going, you can go down all of these. Notice this one. Oops, I thought I was on highlighter, and I wasn't. I just scratched it out. My bad. Notice this is less than 1, so that is obviously a decay. And it's a loss of 75%. I'm sorry, loss of 25%. It has to be because we just figured out, if you look up there, okay, on that one, we figured out 1 minus 0.025 is 0.75. So that's what we have. So this is actually a loss of 25%. Okay, so use that knowledge there to figure it out. I'll do one more with you right here because I want you to have that. But if they tell me my initial value is -5, so I know I got y equal -5, my loss of 94%. So in essence, in here, I'm saying 1 minus 0.94, and it's going to have an x. Now, if I simplify it, it would be 0.6, no, 0.06, right, if I subtract it out. So it's always in that form. That x is always there. So you try the rest of them and then just check your answers on Plus Portals with the rest of those. Okay, on this last part here, number 9, the equation models the salary of an employee who receives an annual raise. Give the meaning of each number and variable in the equation. Well, if you remember we know the basic form of the equation, then this value right here is the initial value, okay? That's what they're starting with. So that's their initial salary. That's how much these guys are getting paid if this is their salary. It's what they're starting with. What does the next little thing mean? This 0.04. I thought I was on highlighter again. Sorry about that. Okay, this part, what does that represent? That represents the interest, basically, or the raise. How much is it going up? That's our raise. Okay, they're getting a 4% raise. And we know it's going up because it's a plus right there. And then this 1, what does that 1 represent? Oops, again. I keep switching back and forth between these things. You think I'd figured it out by now, right? That 1 represents the 100% of their initial salary. Okay, so that's whatever their current salary is. 100% of current salary. Oop. Okay. Let's see. The next part, they're asking you to figure out on the table here. A ball is dropped from a height of 12 feet and is allowed to bounce over and over. The height of each bounce is modeled in the exponential decay model below. Okay, if I were going to write this function, I need all those pieces, right, that we had before. So I need, let's see, we would have the form is y equal to a times, let's see, 1 minus, it's a decay, right, minus, so 1 minus r to the x power. Okay, so do we have ordered pairs? Do we have a y and an x? Yes, we do. Do we have an a? Yes, we do. You just might not realize what it is. A is what you started with. Where are they starting? They're starting at a height of 12 feet. How do I know? Bounce 0. Okay, so right now I know A is your 12. Okay, so what I'm going to do is I'm going to pick this as my ordered pair, just because it's smaller numbers, it's the easiest one, and I'm going to plug that in and solve and find out, well, what is R? You know, because that's important. So I have 7.8 equal to 12, and then in parentheses, 1 minus R. 1 minus R to the x is 1. Okay, so if I solve this equation, what is 7.8 divided by 12? And that is 0.65. 0.65 is equal to whatever this is. So actually, I don't even have to keep going here. I could, but I now know my equation is y equal to 12 times 0.65 x. Okay. All right. So now, eighth bounce. So I'm trying to find out this piece. Okay. So that means all I got to do is plug in x of 8 in my equation. I already got the equation. So y is equal to 12 times 0.65 to the 8th power. And if you do all that lovely math, I believe you get 0.3824. Okay, and 100th bounce, same thing, just plug in 100. Gosh, that must be like massive. Oh, no, it's actually teeny tiny. You get 2.347 times 10 to the negative 18th power, so that's a teeny tiny decimal. That's like almost nothing. All right, so the next part is graphing. I'm not really worried about that because I'm not going to ask you to graph on the test, but you're welcome to go ahead and do that just so you kind of have a familiarity with how it works. And then now let's look at just this, look into what we're doing or we'll be doing after the holidays when we are working with radicals and we start working with trig and all that. It's going to be like super fun, y'all. It's going to be amazing. So what they want you to remember is back in geometry, you should have learned 2 basic triangles, okay? So I'm going to do the easy one first. Remember if you had a 45-45 triangle, then the relationship between these sides, if this was 1, this was 1, this would be square root of 2. Okay, you should have remembered that from last year. As far as, not last year, year before. The other one, and I'm going to try to draw it like the one I see here, okay? Oh, that's so not the same. Okay, so this one would be 30. This would be a 60-degree angle. That's 90. So the relationship here is 1, 2, square root of 3. Okay, it's hard to remember which side is which. One's easy because it's the smallest side. The hypotenuse is your 2, it's longer. And then square root of 3 is the other side. How do you know which side's longer, 2 or square root of 3? Sometimes that gives people trouble. But remember, square root of 4 is equal to 2. So that means square root of 3 has to be smaller than square root of 4 because it's a smaller number. So once you have this relationship in your mind, if you know this already, then you should be able to easily figure out the relationships of the missing sides based on just proportions, basically. So if I look up on number 16, if it's 1 here and then 4 on this piece, these are matching sides here, okay? There's a relationship there. So what they do, they said times 4. So that means I got to do times 4 for all of these. So x must be 8 and y must be 4 square root of 3. All I'm doing is saying times 4. Now looking at the 45, if this side is 2, then this side also has to be 2. And then x would have to be 2 square root of 2. Remember when you're multiplying radicals, inside times inside, outside times outside. Now I'm going to let you work the other two. No, I'm going to go ahead and help you with those because they asked me about number 19 in class. So this one, if this is 7 square root of 2, this must be 7, this must be 7. Let's draw it out. Since this one looks a little different, let's draw it out and make it match. Okay, so I know this would be 1, 2, square root of 3, right? If this one's 60, this would be 30. So look at this side compared to this side. What did they do? They multiplied by 5/2, right? So that means, no, let's see, if I'm going from there to there, we're multiplying by 2/5, right? If I have 5/2 and I got to get to, I'd have to multiply by 2 over 5 to get to 1. So I'm multiplying by 2 over 5. So that means, oh wait, I'm going the other direction. Scratch that. Let's go the other direction. Sorry about that. If we are going from there to there, they multiplied by 5 over 2, so I'm multiplying by 5 over 2 to go up that way. So y would be equal to 5 square root of 3 over 2, and x would be just 5, because we multiply in 2 times 5 over 2. All right, very good. I don't think there's any more. No, we're done. Yay.